Hello again, astro enthusiasts. Welcome back. This is the lecture material that would have been presented on Thursday, April 2nd. We have lots of exciting stuff to go over today, so I'm very excited about that. Let's begin with a short review question. Here it is. The question is this: what is that star right there doing in the center? What's happening to that star in its very center? So if you'd like to answer it, you can pause and come back and we'll talk about it. Your choices are: is it burning hydrogen in the core? Is it an inert helium core but hydrogen burning in the shell? Or is helium burning in the shell with a hydrogen burning shell around it? So pause it, make up your decision, come back, and we'll talk about it. Okay, we're back. All right, so recall this is an HR diagram of a globular cluster. This is M55. And there are lots of interesting parts of this diagram, but all of them are fairly easy to recognize now. You've got the main sequence, you've got the red giant branch, you've got the horizontal branch. This horizontal branch is way over here. Sometimes they're over here, sometimes they're over here, sometimes they're over here, depending on how much mass was lost as the star was in the red giant branch phase. And this, you can actually see, is the asymptotic giant branch. Let's talk about all these phases in turn. And the main sequence is where you're burning hydrogen and helium. If this arrow had pointed down here, it would be hydrogen burning in the core. It is not. This is the stage after it runs out of hydrogen in the core, where it's still burning hydrogen in the shell as it climbs up the main sequence. So this is inert helium core. You're not burning helium, but you are burning hydrogen in a shell around that inert helium core. It will get all the way to the top of the red giant branch. The helium flash will occur, and then it will move very quickly down to this region, the horizontal branch. And the horizontal branch is the helium burning main sequence. That's where you're burning helium in the core, and you're still burning hydrogen in a shell. And if it had been pointing to this, that would have been that, would have been C. When it runs out of helium in the core, it moves back up and to the right along what's called the asymptotic giant branch. You can really see it here now. This branch is an asymptote to this branch. That's why we call it the AGB, or the asymptotic giant branch. If the arrow had been pointing there, there is no arrow for it, but the answer would have been an inert helium, inert carbon core with a helium burning shell around it and a hydrogen burning shell around that. So you can see all stages of stellar evolution in a single cluster, which is what makes them, one of the things that makes them so useful. Okay, we also off at the end of last time, basically just going over this whole diagram again. I'm not going to go over it in detail, but you can see. So again, these are different kinds of pictures. This is a snapshot showing a whole bunch of stars at different masses at the same age, all of them the age of M55. This path that you see here obviously is a cartoon, it's not really data, but this shows a life track of a single mass star at lots of different ages. And so these are fundamentally different ways to think about it. This is at a constant time at various masses. This is at a constant mass at various time, and watching how it goes through all the stages that we know it will go through. Okay, so we left off at the end of class last time talking about white dwarfs, planetary nebulae, and the things that are left behind, which are the exposed cores of these low mass stars we talked about earlier. And the exposed cores of these low mass stars are white dwarfs. They are mostly carbon and oxygen, and they are extraordinarily small, like the size of the Earth, extraordinarily hot, 100,000 Kelvin plus, and extraordinarily dim. And that's why they appear so much far below the main sequence on the HR diagram. Here is an example of one of those. This is the brightest star in the sky, Sirius. It is not a white dwarf, but it turns out that Sirius is a binary star. Excuse me. And when you look at Sirius as a binary star, its companion is so much fainter than it that you can't even see it on here. It's possible that's it, but I don't even think that's it. I think it is like right there. So faint that you can't even see it because Sirius is so bright. Again, we know that the Sirius is a binary system in part because of the spectroscopic binary system and watching it orbit and the spectral lines moving back and forth. But if we look at the same star in the same image in the X-ray, a much higher energy photon, well, a normal star like Sirius is way fainter in the X-ray than it is in the visible. But a really, really hot star like Sirius B, which is a white dwarf, is much brighter by contrast in the X-ray by comparison. And so, yes, Sirius is still brighter than this star in the X-ray, but they're comparable now in brightness. And you can see on the right that that Sirius B must be a much more hot object than Sirius A because it's so much brighter relatively in the X-ray than it is in the visible. If you remember back to our black body radiation curves. So that's a picture of a white dwarf right there. It's right next to the brightest star in the sky. And you can see it in very short wavelengths. Okay, here's a question about white dwarfs though. If you could take a white dwarf, let's take a teaspoon down to land on a white dwarf, which you couldn't because the density and the pressure and the gravity would crush you. But let's say you could land your spaceship on a white dwarf, take a teaspoonful of white dwarf material and bring it back. How much would it weigh? How much would 1 cubic centimeter of white dwarf material weigh on Earth? And when I say weigh, I really mean what the mass of that thing is, because as you know, that's different than the weight. I said weigh, but I really meant mass. Okay, let's go ahead and try to figure this out. Let's go back to my actual whiteboard over here. You can see me. So first of all, what does a 1 centimeter thing look like? Well, here is a 1 centimeter thing. That's a normal plain dice. It's about 1 centimeter. So that's what we're talking about. You don't believe this is actually a little bit bigger than a centimeter. You can't see that at all, but trust me, this is a little bit bigger even than 1 centimeter. So this is the thing to have in your mind when we're talking about this. Obviously, this doesn't weigh very much, but how much would 1 cubic centimeter of white dwarf material weigh? Well, let's think about that. We know that density, this Greek letter rho, is equal to mass divided by volume. We know that in this case, we know what the density and the volume is. The density is 10 to the 9, a billion kilograms per cubic meter. And we know that the volume is a centimeter by a centimeter by a centimeter. And so the volume is 1 cubic centimeter. That's what this thing is. It's a cubic centimeter. Okay, so we can solve this thing for mass. We know the volume, we know the density, we know the volume, we can solve for the mass. Let's just do some algebra first. We multiply both sides by V. The V's cancel out here. We get mass equals density times volume. Great. Well, our density is 10 to the 9 kilograms per meter cubed. And our volume is 1 cubic centimeter. Now, the problem is our cubic centimeter is not going to cancel our cubic meter. So we need to do the unit conversion. We need to know how many centimeters there are in a meter. Specifically, we need to know how many cubic centimeters there are in a cubic meter. Well, I happen to know that there are 100 centimeters in a meter. So I can make this unit conversion go. Again, I've got centimeters on top and meters on the bottom. And I know, so I want to do the opposite. I want a number that's going to be in kilograms. So I need to make these centimeters and meters go away. So I need something that has meters on top and centimeters on the bottom. And I know that in 1 meter, there's 100 centimeters. Now, that doesn't get rid of all 3 of these. In fact, we need to cube this whole thing to get meters cubed on top and centimeters cubed on the bottom. Well, one meter cubed is 1 meter cubed. 100 centimeters cubed is 100 cubed centimeters cubed. This shouldn't be equals. I'm doing this a little bit backwards, but you get the idea. 100 cubed, again, when you cube something in the root, 100 is 10 to the 2. When you cube it, 10 to the 2 times 10 to the 2 times 10 to the 2, 2 plus 2 plus 2 is 6, is 10 to the 6 cubic centimeters. So there are 1 million, if you could line these up, a cubic meter is really big. It's bigger than this whole desk. There would be 1 million of them, of these dice, that would take to fill that entire volume with these things. 100 by 100 by 100. Okay, so let's see what we've got. We've got 10 to the 9 kilograms per cubic meter times 1 centimeter cubed times 1 meter cubed divided by 10 to the 6 centimeters cubed. All these units go away. And all we do then is really 10 to the 9 times 1 divided by 10 to the 6. 10 to the 9 divided by 10 to the 6. These are really easy. You just subtract the exponent. That's 10 to the 3. That is the mass. 10 to the 3 what? Well, we've gotten rid of all these units but the kilograms. This is 10 to the 3 kilograms. Great. Is that a lot? Yes, that is a lot. This is, what is this? 10 to the 3 is 1,000 kilograms. A cubic centimeter of white dwarf material, a teaspoonful of material of white dwarf, has a mass of 1,000 kilograms, a metric ton. I would not be able to hold this in my hand. It would be breaking through my hand and going to the floor. That is an extraordinarily large density. That's what that means. The density is very high. So a very large amount of mass fits into a very small volume. So that's one of the cool things about white dwarfs, is they're extraordinarily dense. All right, let's go back to the slide. All right, so we're at 1,000 kilograms is the answer to this question. And this is the ultimate fate of the sun. This is what the sun will ultimately be. It will get to helium burning eventually. It will become a red giant. It will begin burning helium. It will run out of helium in the core, and it will never get hot enough at the core to burn carbon into something else. And so this is the ultimate fate of the sun. It will become a planetary nebula someday. That planetary nebula will have a white dwarf at the center. That white dwarf no longer has any energy sources available to it. That white dwarf will cool off for eternity. And this thing is degenerate in the same way that the center of the sun was degenerate when the helium flash happened. It has roughly constant temperature, roughly constant density, and electron degeneracy is what's holding this thing up. The fact that these electrons don't want to be squeezed too close together. Now, if you wait a very, very long time, maybe longer than the present age of the universe, you've got a thing that's about the mass of the sun. In the sun's case, it will be a little bit smaller, less massive, that is about the size of the Earth and made almost entirely of carbon. Eventually, this thing will get cool enough that crystalline structures will start to form in this giant carbon thing. What do you think will be the case? What will be the result? What is crystallized carbon? It's diamond. This thing will basically be one single diamond once it cools off completely, almost the mass of the sun and the size of the Earth. You know, if you do want your business venture, here's one. Go to the nearest white dwarf and mine it for diamonds. All I ask is a 10% cut of whatever you bring back. So here is the final definitive. Let's pause here and just reflect on all of the stages of a low mass star's life post main sequence. We start here on the main sequence. We're burning hydrogen in the core. That's the sun now, 4.5 billion years after it formed. Again, this is following the sun. This is just not a star. This is a star the mass of the sun, the sun. In about 5 billion, 6 billion years from now, it will run out of hydrogen in the core. It will move up the red giant branch in a few 100 million years. Eventually, it will get hot enough and dense enough at the center that it's hot enough to burn helium. That helium burning happens all at once. The sun will immediately become less luminous and hotter at the surface. It will shrink back down to be a yellow giant. This is the helium burning main sequence. It will spend some time here in the helium core. Once it runs out of helium in the core, it will ascend back up the asymptotic giant branch. It will eject its outer layers in a planetary nebula, and then end its life down here as a white dwarf, where it will just very slowly over time cool for all time. There's no fuel source left for the white dwarf. It will just get cooler and dimmer over time. Okay, that ends our low mass star discussion. We will come back and talk about the stellar evolution for high mass stars in the next video.